Jingxi to share his content.
All right. Yeah. Hi, everybody. And we are coming here for a presentation by Jingxi Xu. He did his PhD at Columbia, work co-advised, right? I think by Shuran Song and Matei Chokali, who are both like leaders in the area of robot manipulation, learning, doing amazing things with manipulators in general. Jingxi has done some really exciting work in that space, also looking at tactile information and how to do control and manipulation with that information. And he is currently at Boston Dynamics.
Ray.
The Ray. Oh,
yeah.
Boston Dynamics. Yeah, Ray.
VDI.
At
This one, funny.
the Robotics AI Institute. Is that the right saying?
Yes,
Or,
very aggressive.
because then it should be
Robotics and AI Institute.
Oh, so it's Ray with a double I. It should actually. So these guys are, I think, as confused as I am about their naming. But so I'm very excited to see your presentation.
Thank you for the kind words and introduction. So I'm gonna go ahead and share my screen. Right, can everyone see my screen?
Yes.
Can you guys see the slide, the first page of the slide?
Yes.
Okay. So yeah, hi everyone. I'm Jingxi, and I'm very excited to be here to present for AI2. And thank you all for taking your time to drop by on a Friday afternoon before the long weekend. I really appreciate your time. So for small clarification questions, we can ask as I present, but for longer discussion questions, we can leave it at the end. And also, because I can't see people's face, I can only see the presenting screen. So if please stop me if there are any problems or questions. Okay, so I'll get started. Today's talk, I wanna talk about some of my previous work in robot learning, specifically how to address the sparsity and scarcity issue in robotic data. So I want to start with some of my own experience, what my own journey is entering robotics. So when I first came to Columbia, I didn't know that I want to work in robotics. So I worked with different groups on pure learning and pure vision problems. And then I started collaborating extensively with Professor Peter Allen on a wide range of different applications. So I worked on motion planning, visual navigation. I also worked from dynamic grasping to IL versus control. And then I realized, I think one of the key challenges which make robotics so unique, so different from vision and language, is the challenge of data, which is the lack of data we have in robotic applications, which I think most of you guys will agree with me. And I oftentimes use this spectrum to see how much data do we have for different AI applications. And on the left side is the data data sufficiency, and on the right side is data insufficiency. Now, for language and vision applications, it's definitely on the more sufficient side with relatively more sufficient data we can use, especially from the internet. And that's why we have amazing applications such as ChatGPT, DALL-E. And when you move to robotics, things become trickier. So in robotics, oftentimes we need specialized or customized hardware to do the job. And this hardware requires specialized knowledge or expert domain knowledge to operate, meaning that it's really hard to collect data at large scale with this device. But luckily, sometimes we have simulators, and I'm a huge believer in simulation. And if we formulate our problem smart enough, and then it becomes simulatable, then we can actually enable large-scale training inside simulators. However, for some applications in robotics, simulation is very hard. For example, to simulate raw tactile signals or to simulate granular media, it's very tricky to have good simulation for these applications. So it's more trickier. It's slightly trickier to do data collection. What's even more challenging is when you want to collect data from human subjects. And in these applications, such as human brain signals or applications that use muscle signals, there's no simulation at all, meaning that it's even harder to collect data in these domains. And further to the right, the most difficult case for data collection, I believe, is when you want to collect data from subjects with impairments or disabilities. It's already hard to collect data from human subjects, let alone collecting data from people with disabilities. So I think that's the application domain where data collection is the most challenging. And oftentimes when we look at the data problem in robotics, we look at it from the quantity of the data from that angle, and that gives us a data scarcity issue, meaning the sheer amount of data we can collect is very limited. However, there's another angle to look at this problem, which is from the angle of the representation of the data or the quality of the data, and that will give us the data sparsity issue. And that means there's a large proportion of empty space or non-relevant information in the data we collected. And this is because robotics is the science of interaction. So we have a piece of software or algorithm embedded in a piece of hardware, and the hardware is making active interaction with the world to collect useful information. And then the gap or the lapse between two consecutive actions make the robotic data inherently very sparse. So in this talk, I want to focus on two domains. So I want to talk about selective works from tactile manipulation and rehab robots, because I believe these two domains are perfect examples of how robotic applications suffer from data sparsity and data scarcity issues. So tactile sensing is a very powerful modality, but at the same time, it's challenging to use because it's active sensing modality. And every time you contact the target object, you only get sensing around the local area of the contact, which makes tactile signals such as locations and normals inherently very sparse. Now, for rehab robot, as I said before, it's basically, I think, the difficulty of data collection to the extreme. So I've been working for a long time with stroke patients, and it's really hard to collect, to schedule session with clinical experts with stroke patients to collect data. And even for the precious data collection time, there's a huge setup time, and patients get fatigued very easily. So it's very, very challenging to collect enough data to make rehab robot work. So this will be the two domains I want to focus on today. And I will start with the first domain, tactile manipulation. And I'll talk about how we address the data sparsity problem by utilizing simulation and model-free RL to learn efficient tactile-only exploration and manipulation policies. So in this line of work, we go from 2D problems to 3D problems. We go from identification to manipulation, and we eventually go from above the surface to under the surface. So I will start with, due to time constraint, I will start with Tandem 3D, which builds on top of the co-training framework in Tandem and extends this to 3D space. So this is inspired by humans' capability of using tactile sensing, because we humans are experts at using tactile sensing. We can put our hands into our pockets and retrieve a particular object without looking into the pocket, such as a coin. Now, we want to ask if a robot equipped with the tactile sensor, can it do the same? So we are trying to identify a particular object with as few actions as possible. So not only we want to identify the target object, but also we want to do this very efficiently. So that's the goal of this project. So before I go into the setup of this particular project, I want to take a quick detour and talk about the tactile finger we used in the tactile projects that I'm going to talk about today. So this is the disco finger, and it's developed in our lab. It has light emitters and receivers on the skeleton. And then when you touch the gel, you're going to change how the light transmits inside the gel, and consequently change the light received at the receivers. So there are 30 pairs of light emitters and receivers. So this gives us around 900 dimensional raw tactile signals. And this is a visual of how the signals look like when you touch somewhere on the finger. And then we can train a machine learning model that can regress from these 900 dimensional signals into contact locations and contact normals and contact force. And this regressed information will be the information to the policies that we'll talk about today. Okay, so going back from this detour to this particular project, so we mount this tactile finger on the UR5. And a key advantage of this tactile finger is that it has all-around sensing coverage. So it can sense touch from all directions. And then we'll put this target object, which is unknown and in a random position and rotation, in the workspace. And then the robot basically drives the tactile finger, poking the target objects, collecting a sequence of contact locations and normals, this sparse information, and then try to identify this object out of 10 YCB objects. So here are just 4 examples of the information that the robot collects. So I have a very quick question to the audience. Can you identify these objects based on this sparse information? Anyone wants to give it a try?
So the red dot is the touch point, and then the green is the normal.
Correct.
Right?
Yes. Yes.
No, I can't.
And third is the tool, I think.
Which one?
Third is the.
The third one is the drill, I think.
Third one is the drill.
Yeah.
It is the drill.
Okay.
No?
Awesome. Good job.
Okay. Anyone else? Or I'm gonna review the answer.
Everyone seems
Okay.
to be spam.
The first one is the stand. Okay, I'm gonna review the answer.
Yeah.
Wait. Oh, okay. So you guys are actually right. The third one is the drill. I wasn't expecting you guys to be correct, but okay. The point here is I want to show that with very little information, it's very hard even for humans to identify these objects. But 10 and 3D can recognize these objects using only touch with very few actions. So how did we achieve this? Again, the challenges are tactile sensors are active sensing modalities, and they only gives you very local and sparse information. So in order to approach this challenge, we formulated the problem as a model-free area problem so that we can learn an efficient exploration policy to judiciously choose the next action. So in our formulation, we design a 6-stop action space. So at each time step, the robot can choose from X, Y, Z, row, pitch, yaw, to either increase or decrease for a small step. So this gives us 12 discrete actions. And then we identify 3 key components for this task. The first one is the encoder, which encodes the sparse information into a 3D representation. And then the discriminator will look at this representation and predict the identity of the object. And then finally, the explorer will look at this representation and guide the exploration, will output the next action to move. So specifically, the fingers contact the target object, it collects a sequence of contact locations and normals. We first rearrange them into a point cloud. And then this point cloud is passed through two PointNet++ architectures to generate the 3D representation. We choose PointNet++ because it's permutation invariant, and it can also handle different length of points. And this representation will be passed to the discriminator. It will predict identity with a confidence estimate. And if the confidence is larger than the threshold, it will terminate this episode with the final prediction. Otherwise, the explorer will look at its representation and compute the next action for the robot to move. Despite that, we have a distinct decision-making policy and exploration policy. Their training is actually highly interleaved. So we model the discriminator as a CNN and train it with supervised learning. And we model the explorer as an IR agent and train it with PPO. So during this co-training process, the discriminator will provide termination signals to the explorer. It will terminate when the confidence is large enough. And then when we are training the explorer, it will collect a label data set of the point clouds with their ground truth identity. And this label data set will be used to train the discriminator. So during this co-training process, they co-evolve, they change each other, and then they eventually converge. And the whole pipeline is trained purely in simulation and then sim-to-real transfer onto the real robot. And let's show some of the policy in action. So the object is placed in an unknown position. And then the finger will visualize the predict distribution over the 10 objects. Will also visualize the point cloud representation. And the finger collects a sequence of sparse information, and it gradually moves to the most discriminative area of this object. And for this object is the picture handle. And through a small swing motion, it gets a very discriminative point on the handle of the picture, utilizing the full sensing coverage of the sensor. And after another discriminative point on the handle, it quickly converges to the ground truth identity of this object. And this time it takes 37 actions. And this is another example on the power drill. So this time it gets a very discriminative point from beneath the drill, and then it quickly converges to the ground truth identity. And this time it takes 9 actions. So to summarize this part, yes, we have the data sparsity issue in tactile sensing, but Tandem 3D utilize active exploration to tackle the problems by meticulously choose the next action to take to collect the most useful tactile information. So that's the Tandem 3D work. Now we want to move to a more challenging environment where vision is basically out of the question. So this work is what we call geotact. And in this work, we're trying to retrieve objects buried completely inside granular media with only tactile sensing. Again, we still have the challenges of local and sparse information of tactile signals, but also because of granular media, in such a sensor-deprived environment, we also have extra large uncertainty and sensing noise. In addition, this environment also requires certain properties of the hardware. A lot of the vision-based, camera-based tactile sensors, the Pioneer work, even though they have very high resolution, they have boxy form factor, which will induce high drag when they move inside granular media. Also, the tactile sensing they gave, they don't cover the edge and corners. So, but in granular media, you really need the full sensing coverage. So there are some specific hardware requirements on the sensor we use. We borrowed the idea of pushing from a lot of previous work. So many previous work show that pushing is a very efficient technique to reduce uncertainty and increase grasping robustness. But most of them show this technique on tabletop or open air environments. In this work, we basically argue that pushing is efficient techniques also in granular media. It reduces uncertainty, increases robustness. It also is a great technique to funnel the object to a graspable pose. However, designing a heuristic-based pushing behavior isn't trivial. So again, we formulate the problem as model-free RL and utilize simulation for large-scale training. And we hope that the pushing behavior can emerge by itself through the design of the action space. So our action space is a 4-dimensional vector, where the first 3 elements is the discrete change in x, y, and theta direction. So our finger, because our finger moves in a 2D plane. And then the last element indicates whether the exploration should be terminated and the finger should close and grasp the target object. Any questions so far? Because I can't see people's face. So
No.
Okay, great.
Sounds good.
So
far.
Perfect. So I'll continue. So the observation to our policy is a sequence of contact location, contact force, and past actions. However, different from open air environments, in granular media environments, there are actually 2 different kinds of contacts. The first contact is what we call ubiquitous contact. And this is the contact you get from between the finger and the granular beads. And before your finger started pushing the target objects. And the second type of contact is what we call pushing contact. And that's the contact you sense when the finger has started moving the target object. So we believe only pushing contact carries important information for our policy. So we use the filtering techniques to only keep pushing contact to our policy. And also, very importantly, we have a curriculum training strategy. Again, the full pipeline is trained in simulation and sim-to-real transfer onto real robots. So we want to reduce the sim-to-real gap. So we think it will be very useful to train in simulated granular environments to simulate the behavior of the target object when it moves inside granular media. But again, like as we briefly mentioned before, simulating granular media is very time-consuming, very inefficient. So we want to reduce the time in granular media by bootstrapping our training on a tabletop environment. So in this curriculum strategy, we first train a push-to-grasp behavior on a tabletop environment. And then after it converges on tabletop, so basically the finger just push and form a group grasp and lift the target object. And after it manages this task, we load the converged checkpoints into simulated granular environments to fine-tune inside granular media environments. And then eventually, after it converges in granular media environments, we'll zero-shot transfer onto the real robot. So this is our curriculum strategy. Finally, this is our hardware. We mount the disco fingers on the parallel gripper. Again, the full sensing coverage of the disco finger works really well with the granular media environment. And the cylindrical shape also reduce drag inside the granular media. I want to show some of the policies in action. Well, in this demo, we'll visualize the contact location and also the contact force. So this is where we bury the chocolate box. So our policy initially detects a fake pushing contact, even though it hasn't really contacted the target object. So it starts to react to this fake contact until a true contact happens. And then it starts to correct its own behavior. And then through a series of interaction, it correctly form a group grasp and retrieve the target object. So this is another example on the screwdriver. So the screwdriver is actually a very hard object to grasp. It's very long and very thin. However, the policy, through a series of pushing interaction, form a good grasp and successfully retrieve the screwdriver. When we train the policy in simulation, it's only trained on 7 objects with primitive shapes. However, the policy actually works on a larger range of objects. So these are some random objects we chose from our lab, and we just threw them into the granular media, and then we asked the policy to retrieve them from the granular media. And the policy is able to generalize to these objects within 3 attempts. So sometimes it does use up all 3 attempts to be successfully grasping these objects. It's always fun to look at failure cases. One of the most common failure cases is when there's a thin layer of granular media getting stuck between the target object and the finger. And because of the very low friction of the beads and 3D printed object, it often slides off. Another very common failure case is when we are trying to grasp cylindrical or ball-shaped objects. Because our finger is also cylindrical, so imagine 2-cylinder grasp ball. It's very hard, and the ball is oftentimes squeezed outside the finger. So we believe this is a limitation of the parallel grippers, and if we have multi-handed fingers, grippers, this will be less of a problem. So to summarize this part, GeoTact utilize model-free RL and simulation to learn an emergent pushing behavior to efficiently explore and grasp target object under sparse tactile information. Nice. So we covered my line of work in tactile manipulation. Now I want to switch gear. Feel free to ask questions if you have. Now I want to switch gear to rehab robots. And I want to talk about how we handle the data scarcity issue in rehab robots. So while data sparsity in tactile manipulation focuses on the quality of the data, now we want to switch to the quality of data. So during my PhD, I collaborate with the Columbia Medical School and mechanical engineers. So our lab developed a wearable device to help the stroke subject open their hand. And we have to train machine learning models that predict their intent such that the wearable device can provide appropriate assistance. In this line of work, we explore different paradigms that ranges from semi-supervised learning to meta learning to generative AI. We go from only being able to handle intra-session drift to also being able to handle inter-session drift. And I'll explain the difference in these 2 terms later in the talk. We also go from only being able to use low capacity classifiers to finally being able to use high capacity classifiers. And the work I want to focus on in this domain is ChatEMG. But I'll also touch on the 2 projects before ChatEMG in this talk. Again, the goal is to train inter-inferral classifiers with very minimum data collection because it's really hard to collect data from people with disabilities. Before I go into details, I want to share some background about this domain. So 800,000 people have stroke a year in the US, and a majority of them will XP impairments. Less than half of them will recover full function. A lot of tasks that healthy subjects, we take for granted are impossible for stroke subjects. And this is a stroke subject attempting to pick and place this wooden block, which is very hard, is impossible. So our lab developed this wearable device on the right. It's a motor-driven exoskeleton. It has a motor. It is a tendon-driven device, and it also has an EMG armband. So the EMG is short for electromyography. You can think of it as you're measuring your muscle intensity or muscle activities. The goal or the machine learning job, the software job, is to develop machine learning models that can predict the user's intent from the sensor reading. And if the model thinks they want to open their hand, the model drives the tendon and extend their fingers. And if the model thinks they want to close their hand, the model releases the tendon and the patient can use their own strength to close their hands. So the population we study in this line of work, they lose their ability to open their hand, but they still have their residual motion to close their hands, which is a very common stroke after effect. This is the armband we use. It has 8 electrodes surrounding the forearm, producing 8-channel EMG signals at 100 Hz. This is a demonstration on healthy subjects. For stroke patients, the change in the EMG signals is much subtle. That's also why it's much more challenging for stroke subjects. We already know that it's really challenging to collect data on people with disabilities. And what makes it even more challenging is there are huge variations or drift in EMG patterns across conditions, sessions, and subjects. So what do I mean by these different terms? So a condition is basically a combination of the arm position and the status of the device. So for example, here are 3 different conditions. Arm on the table or device off, or arm off the table, device is off. And a session is a single use of device between donning and doffing. So basically, a patient joins our session, come to the hospital, we put on the device, we do our experiments, and they take off the device, and that's a single session. It's easy to understand because for different subjects, due to different neuromuscular impairments, they demonstrate very different EMG patterns. But even for the same subject, if they come in different days for different sessions, there's a huge drift in EMG signals as well within sessions, across sessions. Now, even for the same subjects, for the same session, if they move their arm to a different location, there is also the huge EMG signal shift. And here's an example of, for different conditions, even for the same intent, you can see how different the EMG patterns are, even for the same intent. And this is more pronounced for the drift across sessions and subjects. For the drift that happens within a single session, we call it intra-session drift. And for drift happens across sessions, we call it inter-session drift. So normally, yes.
Sorry, just a quick clarification question. The different lines in each of these plots, are these different runs or different dimensions of the EMG signal?
Yes, these are different because we have an 8-channel EMG sensor. So yeah, so the x-axis is time. So the y-axis is basically in intensity, and different lines are just different electrodes.
And if you would do multiple repeats of, let's say, arm on table, device off, there would also still a huge variability among those, right? Or would they be?
Yes, yes.
Okay.
Which is naturally like you will have different patterns for different intents.
Yeah.
So here I'm showing like even for the same intent, if the arm is performing the intent moves to a different position, like the signals, the pattern will also differ. Does that make sense?
Yeah.
Okay. Thank you for the question. Right. So because of the huge variation, normally the model does not generalize. So when we train a model on a single session of patients, it does not automatically generalize to a new subject or patient. So what this means is every time a new patient joins our session, we have to implement the full data collection protocol again, which is a lot of burden on the stroke subject. So in order to relieve this problem, the first paradigm we turn to is semi-supervised learning. And the idea is really straightforward, which is we want to utilize unlabeled data. Now, in this work, we basically only collect a small data set from the new session or patient. And then we train an initial model, we deploy the model, and then we ask the model to adapt to new unlabeled data. And this means that we'll need a heuristic to label the unlabeled data. And we don't want, I don't want to go into details here. Basically, the heuristic we use is a discriminant-based semi-supervision. And by utilizing unlabeled data, it does work better compared to baselines that do not utilize unlabeled data. However, it has its own problems. So because we are relying on heuristic, this heuristic does not generalize to the drift across sessions of patients. And also, this semi-supervised learning pipeline requires the classifier to be able to run fast online update. That means it does not work with any type of classifiers, especially for high capacity models. And then the second paradigm we study is meta-learning. So in this paradigm, we formulate the whole intent inferral problem as a multitask learning problem, and we treat each session and subject as a single task. The goal is to learn some intermediate representation that is fastly adaptable to a new task. In this way, it does generalize to new sessions of patients. But again, meta-learning has its limitation, which is it requires the tracking of higher order gradients, and it also only works with gradient-based models. This means that this method is not classifier agnostic. So at the end of the day, we really want a paradigm that is able to generalize across different sessions of patients, and also can work with a different type of classifiers, any type of classifiers. That's why we eventually turn to generative AI methods, and that's why we study chat-EMG. So what is chat-EMG? Chat-EMG is an autoregressive generative model that can generate synthetic EMG signals conditioned on prompts. Similar in concept to language model where a prompt is an existing piece of text. In chat-EMG, a prompt is an existing piece of EMG signals. And then language model generate the next words or tokens autoregressively. Chat-EMG will generate the next A-channel EMG signal at the next time step autoregressively. The way to use it has 3 stages. In the first stage, we train chat-EMG on a large corpus of offline data collected across different subjects, sessions, and conditions. And we hope that through this generative training, it can learn the general patterns of different intents, such as open, relaxed, or close. And now in the second stage, when a new subject joins our session, we don't run the full data collection protocol again. We only do a very limited data collection from this new context. And then we keep sampling prompts from this limited new data and conditioning on the prompts. chat-EMG generates synthetic data by expanding the prompt to a length where the classifier takes. And then this synthetic data is combined with the original data to train basically any type of classifiers. And then we can deploy the classifiers on the device to help the stroke subjects. And in this way, it can generalize to new sessions of patients. And because the synthetic generation process is completely separate from classifier training, it can work with any type of classifiers. So finally, we take the whole pipeline of data generation, limited data collection into a real clinical environment. And in this demonstration, we are showing onboarding a new subject. So the data from this subject is never seen by chat-EMG before. And then we asked her to perform pick and place. Because without any assistance, it's impossible, which makes a lot of sense. Now we started data collection. So the way we do data collection is we'll give out verbal cues to the subject. We'll say open, relax, or close. And then we'll record the 8-channel EMG signals simultaneously. So you can see now we say open. And because she couldn't open her hands, so you barely see any change in the EMG signals for the open intent. Now we say, please close your hands. And you see that she can close her hands and there are huge EMG changes. And finally, we say, please relax your hand. And that's the only data we collect. That's one round of open, relax, and close data. And then the first demonstration we show is on the cluster trained only with this limited data set. And then because the data is so limited, the cluster never correctly predicts the open intent, and the patient couldn't use the device to perform pick and place, which is very understandable because the data is just so limited. Now, this is the data we collected before. With ChatEMG, what we can do is we can sample prompts from this very limited data set, and we ask ChatEMG to complete the prompts. And now the second cluster is trained with this synthetic data plus the original data. And now you can see the device can successfully open, and the patient can use the device to perform multiple rounds of pick and place motion. And it's not perfect, but it does work much better compared to the previous model that do not use synthetic data at all. And to the best of our knowledge, this is the first time a model trained partially on synthetic data is deployed on a real stroke subject in a real hospital environment. And to summarize this part, in order to handle the extreme data scarcity issue, we use synthetic data generation. So ChatEMG, the gist of it is that it leverages a vast repository of previous data through generative training, but it also remains context-specific via prompting. So to summarize what we talked about today, we talked about how we handle the data sparsity and data scarcity in two different domains. So we learned that even though we have the data sparsity issue in the tactile signals, we can utilize simulation, and we can utilize RL to learn efficient exploration policy to judiciously choose the next action to explore and to manipulate the target object. And for rehab robots, we learned that we can use, not only can we just try to make it work with minimum data by utilizing semi-supervised learning or MAT learning, we can also dream up our own synthetic data through generative AI. The hope is that the lessons we learn from these two domains are also applicable to other domains because the data problems are so fundamental in robotics. At the end, I also want to quickly mention another line of my work, which I spend a lot of time trying to make it work, is dynamic grasping. So we try to make the robot grasp dynamic moving targets through online planning of grasp, which are both motion aware and reachability aware. And in some follow-up works, we study how to learn a meta controller that dynamically tune the meta parameters of each subcomponents in the whole dynamic grasping pipeline. This is some demonstration in simulation. Finally, in the maybe the last 4-5 minutes, I want to talk about what I want to work on in the future. So I want to work on robotic applications that has real impact on people's everyday life under real life constraints. So I think data problem is one major real life constraints we have. And I'm always interested in seeing robots, my algorithms or models deployed on the real hardware, preferably in unstructured environments. And I think one of my main future focuses will still be robotic manipulation. And I believe robotic manipulation is the pearl of robotics. It's one of the most prized and challenging domain in robotics. And I think in order for us to achieve the goal of like generous robots that can manipulate, that can do dexterous manipulation, local manipulation, as humans can do, we need to do works on multiple fronts. And one of the fronts, I think, is we need really scalable data collection pipeline for multimodal data collection. So last summer, I was working at BDI, now called Ray, on just developing a handheld device based on Yumi, adding a tactile sensor, and it can collect basically visual tactile demonstrations. And then with these visual tactile demonstrations, what we can do is to replicate this task on the real robot, and we show that the added tactile signals help it with tasks like task key insertion. Because when you close the gripper, it's really hard for the camera to see what's going on under the gripper. And fast forward to today, after I joined Ray about 2 months ago, we made a very impressive progress. Since last summer, we are developing the state-of-the-art handheld data collection device. And we're also collaborating with people like outside this company to scale up our data collection. So I think this will be an important and interesting area to keep exploring. And when I say scalable data collection pipeline, I don't necessarily mean handheld data collection. I think teleoperation is also a variable, interesting choice, and both of them have their pros and cons. And another front is I'm a huge believer in simulation, and I believe simulation and synthetic data is one of the key to really address the data problem in robotics. I think right now we still have a lot of challenge in simulating, for example, raw tactile signals or deformable objects. If we can really simulate raw tactile signals, I think that can enable a wide range of dexterous behavior. Another thing is multimodal foundation models. I believe utilizing internet data by utilizing large pre-trained models on language or videos will be very important to achieve generalist robots. To the best of all my knowledge, I don't think right now we are at the point where we truly utilized the common sense or the physics that are learned by the large language models. Most of the time, we are still using language as like an indicator of which task to perform. So I think there will be a lot of opportunities to work on this domain. And finally, I think very importantly, we need a very robust and comprehensive, yet easy to spin up evaluation benchmark. Just some simple codes that every lab can just spin up and then associate your model or your algorithm with a number. And then this number can be compared across different labs. I think that will be very useful. And this is something we need to really understand the model we learn, to evaluate the model we train. And with that, I think this is the end of the presentation, and I want to thank my amazing collaborators and thank all the audience for taking your time to attend this talk. And I'm open to questions.
Thank you.
Thank you.
Questions?
Sure. In the rehabilitation setting, have you thought about, it seems like a very natural goal to have continual adaptation. Have you thought about how to extend that kind of few shot learning into the continual adaptation setting?
Like something along the line of semi-supervised learning, like utilizing unlabeled data.
Something like that, but just in the
Yeah.
sense that it would be desirable if the device continues to adapt to the person's signals in situ, right? So how have you thought about how we might approach that?
Yeah, definitely. So one, I mean, like the semi-supervised learning work is along that line. We also tried to develop some unsupervised learning or a feedback mechanism for the patient. So basically, one of the ongoing work we have is we'll provide a button for the patient to provide feedback. So after the model is being deployed, the patient can use the button to basically interrupt the model and then provides feedback. For example, if the model forgets to open, and then the patients can say, okay, press the button and it indicates now when you see this data, you should open your hand. So this is something we are studying right now. And button is basically a very simple and binary feedback mechanism. We can also use language to give more fine-grained feedback on how to adapt online the model. Does that make sense?
Yes, thank you.
Thank you.
One question regarding the benchmarking you mentioned at the end, when you say
Mhm.
every lab should be easily able to do that.
Yeah.
I always see the risk with benchmarks that if they become too specific, that pardon?
People overfit.
Hmm?
Yeah, they start overfitting.
Exactly. So people will
Mhm.
overfit to your benchmarks and present better and better numbers, but mainly because the benchmark doesn't capture enough variability, right? How do you
Yeah.
think we can ever overcome that, especially in the real world?
Yeah. I think it's really hard. This is a very good question. I think we cannot avoid completely people just overfitting to the benchmark. But I think even though people do overfit to this benchmark, it does provide value, even though it overfits. So if you can overfit to a specific benchmark, I think there are definitely things you learned that are useful for you to overfit to that benchmark. And also, I think this benchmark should also be continuously maintained. I mean, when people are at the stage where they completely nail this benchmark, it's probably the time to come up with a better benchmark, which incorporates more challenging task by observing how people how their model fail.
Yeah. Do you
Yeah, that's-
see any potential for like using simulation? Because maybe in simulation, if you get the realism done,
Yeah.
which is a big if, as we know, but
Yeah.
if so, then you can do much more automatic randomization and things like that and make the overfitting to the tasks harder.
I see. I agree with you. I see huge potential in simulation, but I'm worried that right now, given what people can do in simulation, is not challenging enough
Mhm.
for as a benchmark. So I think it will eventually be a benchmark after we make it much better.
Yeah. No, that's a good point. Yeah, it was still not quite there yet.
Yeah. Good question. Any more questions?
If nobody else, I have one question I could ask that's a bit more specific. In the, I think it was the tandem 3D where you had these objects and then the touch points, the contact
Yes.
points on them. It
Mhm.
feels like, and if you put these objects onto that white pedestal, then actually the global position of where you make contact tells you already a lot of information about, for example, the size of the object and things like that, which makes actually the classification much easier than if you would only do it based on shape. Did you prevent it from doing that, or did you give it the global contact point? Do you understand what I mean?
Could you elaborate a bit more?
Okay, so for example, let's say you have two spheres.
Yeah.
And one is like whatever that big, and the other one is twice as big. And by putting the sphere on the pedestal,
Yeah.
you can already identify which of the two it is simply by the first touch based on how far away it is from the pedestal.
Yes. That's true if the location is the same for both. But this is not true for this case because the location is actually randomized. So
okay, so even the location of this white pedestal on which the object is placed is also randomized.
that is not randomized, but because it's connected to the board, but the object, because its object is using Velcom to attach to the cylinder, its location can vary, and the orientation can also vary. So technically, it can only occupy half of the cylinder. But
okay.
So, but inside our training simulation, there's no like this cylinder stand, and the object can basically freedom move inside the workspace as long as you can get a first contact.
Mhm.
So you cannot like put it away such that the robot moves along the diagonal of the workspace and couldn't get a contact. Then that's an invalid episode.
Mhm.
But we does randomize the location. But during testing, we have to like attach this thing to the workspace, so it's limited testing.
Could you imagine having a network that takes as input also object models? Like right now, I guess your network is trained on this specific set
Yeah.
of objects, right? But making it so that you say like, okay, here are 5 object models. Which of those is it?
Yes. So that's an interesting point. I would argue that our model is model-based because during training, we are basically keep loading this object in our RL training. So we are actually using the model. So, but I agree, like if we want to maybe extend this pipeline to not just instance level identification to class level identification, we do need somehow to input more information to the policy. Because right now, like we only have a limited number of objects. What we want to do in the future is, for example, if you have different type of sofas or different type of bottles, can you identify on a class level, right?
Mhm.
I think when we reach that level of difficulty, then we do need to utilize models more explicitly.
Yeah, that makes sense.
I had another question about this work, actually.
Mhm.
I was wondering about the strict necessity of the classifier module, because if the Explorer
Mhm.
module has enough information to do efficient exploration,
Yeah.
shouldn't it also have enough to do discrimination?
That's a very good question. This is actually one of our baseline. So one of our baseline, we just give everything to the Explorer. So the Explorer has to lead the exploration, but also like have to determine when to stop the exploration and what is the output, what is the identity of the target object. So it takes much longer to train because it doesn't, it's not efficient as you separating, you have a separate model of discriminator. We train it specifically with a label data set, right? So yes, that's a good point, but it doesn't work as well as separating these two components.
Okay, thank you.
Is there some connection you could make to like actor critic kind of models in reinforcement learning in general?
Yeah, I think the idea of this is actually somehow from the actor critic setup. Yeah, it's similar in concept.
Okay. Thank you very much. I think we're right on time.
Thank you. All right,
Perfect.
let me stop sharing.
Thank you. So
Awesome. Thank you everyone for joining.
Thank you everyone for your time.
Bye.
Thank you.
Bye-bye.
Jingxi, I'll be in touch.
All right, thank you. Bye.
Okay, have a good weekend.
You too.